How do you tell one bathroom full of statisticians from another? You check the p-value. And yes, we will be checking some p-values. So let's go ahead and start with this problem. We have resting pulse rates for a random sample of 26 smokers, had a mean of 80 beats per minute and a standard deviation of 5 beats per minute. Among 32 randomly chosen non-smokers, the mean and the standard deviation were 74 and 6 beats per minute. Both sets of data were roughly symmetric and had no outliers. Is there evidence of a difference in pulse rates between smokers and non-smokers? Well, we do have some initial evidence, which is just basically subtracting the two means, and they seem to be about 6 beats per minute far apart. And this is what we call our point estimate. Now, we don't know if that's just from random chance or if that is too unusual to say that's just chance that there's actually a difference. So what we're going to do is we're going to perform a two-sample t-test for the difference in means. Our state is similar to before. We're going to do them kind of like when we did the proportions for the differences. So we can just say the first mean minus the second mean. We assume there's no difference, so we say 1 minus the other is 0. Or you can say that mean 1 equals mean 2. Now, the three forms for the alternate hypothesis, they can be mu1 minus mu2 doesn't equal 0. But if you're using a calculator, you'll probably see it in this form. Then the difference might be greater than 0, or the first might be greater than the second, or the difference might be less than 0, or the first might be less than the second. So the top line is how you typically use it when you're calculating your test statistic by hand. The bottom line is more what you would use when you are using a calculator. So let's go ahead and complete state for our smoking example. And our null is that there's no difference in mean pulse rate between smokers and non-smokers, that the difference is equal to 0. Our alternate hypothesis is that the pulse rate, now you got to keep track of which one's bigger, all right? So we're going to say the pulse rate for smokers is greater than non-smokers, all right? So if I take the mean smoking pulse rate minus the mean non-smoking pulse rate, I would get a number greater than 0. Or simply say mean pulse rate for smokers is greater than mean pulse rate for non-smokers. Don't forget to specify what these symbols mean, since I read it to you here, but when you're doing a free response, you should write it. So here I have where mu of S is the average pulse rate for the population of smokers, and mu of N is the average pulse rate for the population of non-smokers. Now, our procedures and our plan and our conditions change a little bit for a two-sample t-test for the difference of means. We still have a large normal sample. Make sure that you check each of the sample sizes. Now, some of you are going to just say large normal check. Sorry, that doesn't work. You have to look at the individual sample sizes and confirm that each one is greater than or equal to 30, all right, for both groups, all right? Or if we know the populations are approximately normal, you're done with the normal condition. You don't have to go any further. If you don't know either one of those things, if you don't have a large sample and you don't know if the populations are normal for both, then what we need to do is to do a check for no skew or outliers by making a histogram or box plot for the appropriate sets of data. So if one of them you know is normally populated, you only have to check it for the other. But in almost every example I've done, you've had to do it for both. All right. Random. Make sure that the data come from two independent and random samples. All right. So if it doesn't say independent or random, you kind of want to include those words in there. Or if they come from two groups in a randomized experiment, you're fine. Now, splitting a sample into two groups is not considered independent, and I have seen that on a free response question before. So you might need to say, well, it's reasonable to assume that they're independent. All right. So if you're really not getting what you need, but it's reasonable to think that there shouldn't be anything wrong with it, say it's reasonable to assume it. Now, when sampling without replacement, sample size for each group is less than 10% of the population, and you would check each sample size. All right. Now, if you're doing an experiment with random assignment, this is not so necessary to check because there's this, I could go into this side thing where you can do different randomizations on how you assign it so you can actually create a sampling distribution. So 10% condition, not really an issue for randomized experiments. All right, now we're going to name the procedure and check conditions in our smoking example. So is it random? It's stated in the problem that the smokers and non-smokers were chosen randomly. And it is reasonable to think that both samples are independent. Large normal, given that both sets of data are roughly symmetric and have no outliers, this condition is met. All right. And see it's written right here. Both sets of data roughly symmetric and had no outliers. So we can say that our conditions are met for this sample, or really samples. All right, now we're going to go ahead and start the do part, the calculation step. And I need to introduce to you the formula for the standard deviation, or really standard error, for our statistic. But first of all, when we had two proportions, we always pull the data together. So we would actually put P1 with P2, and we'd kind of assume they were equal. Well, the null assumes the proportions are equal, and if I know what the proportions are, then we can then say that the standard deviation can be calculated because we know the proportions. Now, for the means, we can never pull, because we'd have to assume that the variances are equal, but we can't do that. There's no link between mean and standard deviation. And there are some times when you could do a pooled t-test. I've never seen it on any of our testing. It might be appropriate in a comparative experiment because they might start with the same population variance, but really, really, really don't ever, ever, ever jump into the pool. Just don't do pooled statistic. All right. So if you have a data list, just to let you know, we're going to go ahead and calculate some statistics. You could run one var stats to get your S of X bar for each group. All right. But usually, honestly, if you're calculating this by hand, they probably gave it to you for each group. Now, we're going to revisit how to calculate the sum of two variances. Remember that variances add. So my variance for X, if I have a difference here of two variables, my variance for X squared, well, that is my variance because that's my standard deviation in there, or standard error, depending on the symbol. And that one is squared. And if we square them and then add them, I get this. But standard error is the square root of variance. So this is actually what you do see on your math chart. All right. So then once we have the standard error for our sample, by the way, this is standard error because we do not know the population standard deviation. Sigma is used for population, S is used for sample. All right, now we can go to our standardized test statistics. So this is the formula that you have on your math chart. And unfortunately, this formula is not on your math chart, so you need to remember it. It's going to be the difference in means, all right, because that's our statistic. We're assuming the difference is 0. That's our parameter. And then we just went over how we got this formula for the standard error of the statistic. All right. So then the last part is doing degrees of freedom and the p-value. So the conservative method, if you're doing it by hand, basically do the degrees of freedom for each sample and use the one that's smaller. So you would do a one-sided p-value would just be your TCDF with your test statistic for lower, then your test statistic for upper. Usually one of these is infinity or negative infinity. And then your degrees of freedom. Remember to double this value if you're doing a two-sided test. So this is really geared towards a one-sided test. Then the other way you can do it, and honestly it's much faster, is use a calculator for a 2-samp t-test. Still write down what we were writing as a name. You need to report degrees of freedom, t, and the p-value. If you do not, this section, it's usually a step called calculation, will be marked incorrect. And that will be like a whole point off of your question if you leave any of these out. So you can have all this beautifully done and leave off degrees of freedom, and this section is marked incorrect. All right. Conclude is almost the same. Now remember, we got to talk about differences, and we always have to talk about context. So Because our p-value is greater than or less than, and remember, use your given alpha, whatever it is. If they don't give you one, 0.05 is reasonable. Then we would either fail to reject or reject H naught. And then we either have insufficient or sufficient evidence that the true difference of means. So make sure that you are specific about that, of your whatever it is we're measuring is either, one is greater than the other, it's greater than 0, less than 0, depending on what your alternate hypothesis is worded as. Now, if you do word your alternate hypothesis in one form, as long as what you write makes sense here, and you reword it, that should be fine. All right, so we're going to complete do and conclude for our smoking example. And here are the values from the problem. We're calculating standard error by hand, and we get 1.444 BPM. And there is our test statistic T, and our p-value is just TCDF of that, which is 0.000168. So therefore, we can conclude that because the p-value is very small, the observed difference is unlikely to be just sampling error. By the way, that first sentence is really interpreting the p-value, and I'm going to revisit that. So our normal conclusion that we're used to starts right here. We reject the null hypothesis because of the small p-value. We have strong evidence that the mean pulse rates for smokers are higher than those for non-smokers. You notice that I didn't just say that the mean difference was greater than 0. I tried to put it in context and have everything make sense there. Okay, so let's take a look at another example. Here are the saturated fat content grams for several pizzas sold by 2 national chains. Is there evidence of a difference in fat content between the 2 brands? So my state part is that the difference is 0, okay, where that's the mean difference, and let me go ahead and put that part in, where this is the mean difference or mean fat content for brand D, and this is the mean fat content for brand PJ. All right, so you can say that they're equal to 0. They don't really tell me a direction, like higher or lower, so I'm just going to say not 0 here. Then we do our plan, which first we say what test method. Well, we're comparing 2 samples and we're looking at a difference in means. So we're doing a 2-sample t-test, and you can actually write this out in the symbols. If you already have this well defined up here, you don't have to do it again here. The first condition we have to check is random. Well, we kind of have to assume both pizza samples are independent and representative of pizzas made by these 2 chains. So I don't have anything in there saying that it meets the condition, so I'm going to say I'm assuming this condition is met. Remember, we can't do the work if the conditions are not met. Then the nearly normal condition, because the sample sizes are small, we have to look at the distributions. All right, and so when I put them up, you can see they're roughly unimodal and symmetric. There's no strong skew. There's no outliers. This looks pretty good. So we're going to say that condition is met. Finally, let's go ahead and do the calculation. So I will do this by hand. And here's my standard error using the formula. There is my test statistic. So you have both of these. All right. And there's my degrees of freedom. My smallest sample size was 15, so I used that one. And the p-value will just be, because I'm trying to go extreme, I could have done the low end or the high end. High end's easier. So I'm doing 4.823 to infinity, which is usually a giant number in your calculator. There's my degrees of freedom. And I'm doing a 2 in front of it because this is a 2-sided test, because I'm saying not equals 2. Now on the TI, this is, here I'll go ahead and show you. We have the data here entered in 2 lists, and I do have a separate lesson on how to do this on the calculator. Go to 2SAMP t-test, and since I have data, list 1, list 2, the frequencies are 1, always have that one unless you have a good reason, and we're just testing that it's not equal to. There's the output. And if I wanted to, I could actually also do a test where I could graph it, and you can see the t-distribution. So that's kind of cool. So we're going to do draw now. And you can see there's the drawing. And it will show you, it always takes a little while because there's a lot of calculation going on. Here, because the p-value is so small, it's just saying 0. And the test statistic is 4.823, which matches what we got before. So on this screen, you can pull off the p-value and test statistic. The problem is this one doesn't have degrees of freedom. Make sure that if you do that, on the output screen, it does show the degrees of freedom there. Okay, so let's go ahead and conclude. Since the p-value is very low, which it is, we reject the null hypothesis. There's strong evidence to suggest that the two pizza brands have different mean saturated fat content. Brand D appears to have more saturated fat on average than brand PJ. See how we're being extra clear on the direction here. By the way, we were only testing, this one was fine. I could have stopped right there. But it doesn't hurt to say what direction it was in. Okay. So you might be asked to interpret a p-value, and we've kind of talked about it before. It's basically a given probability, given that the null is true. So basically, you're assuming that H naught is true, that the null is true. There's a p-value probability of getting whatever statistic you got in context. And make sure you say it's either or higher or lower or more extreme. And then, of course, just by chance. So I'm going to interpret the p-value for the pizza fat content example. And I'm saying, assuming there is no difference in fat content among the two pizza brands, there is a 0.0003 probability of getting a difference in mean fat content of 4.72 grams or more extreme by just chance. Now, I didn't really say higher. Why did I not say higher? Because this is a two-sided test, right? And I need to say higher or lower. But if I say lower, it's kind of weird here. So I say more extreme, okay? And meaning further from 0. Okay, so let's go ahead and look at another example. And we're going to do pulse rates again, except this time we're testing out an exercise device. And we have 10 randomly selected men. They're going to be using it 3 times a week for 20 minutes. Their resting pulse rates, beats per minute, were measured before the test began, and then again after 6 weeks. Based on the results in the table, is there evidence that this kind of exercise can reduce resting pulse rates? So I have the calculator output already right here for a 2-sample t-test, all right? So based on this, first of all, you want to report T, P, and DF. All right, make sure you write that down. I know you can see it on your calculator, but they need to know that you have the critical values here. So looking at our p-value here, we can see that it's not very low. In fact, it's greater than a reasonable alpha 0.05, so we're going to fail to reject our null. There's insufficient evidence that the mean resting pulse rate after is lower than the mean resting pulse rate before exercise. Now, how is that example? Let's go back and look at that. We've got Alan, Brandon, Carlos, and we have before and we have after, all right? So how is this example different than prior examples? Well, each pulse rate in the before column goes with a specific pulse rate in the after column, and so these data are matched. Part of the reason people love working with twins in experiments is because they're matched. So when we're working with matched pairs, we're not interested in just the differences in the means, which is what we just calculated. All right, we found the mean of before, we found the mean of after, and compared them. But because each pair of data is matched, we can actually look at individual differences and look at the mean difference. All right, so matching minimizes the variability from person to person because we're going to have, I think there was a David, we have his before and we have his after, and it takes into account, that's for David. So what we want to do is test the mean of the individual differences. So we will use a paired t-test for the mean of the differences. The state, plan, do, and conclude are pretty much the same, although you do want to kind of say that you do have paired data. All right, so don't forget that. All right, so using the differences in before and after, determine if there's evidence that this kind of exercise can reduce resting pulse rates and interpret the p-value. So first of all, I'm assuming that the mean difference before and after exercise is 0, that it doesn't really change much. So notice before I said mu1 minus mu2 or mu before minus mu after. Here, it's just the mean of the differences. So it's just one mean, all right? We're thinking that we're going to have a decrease, all right? Because I'm doing before minus after. If it really does reduce it, we should see a positive difference, all right? Make sure you clarify where mu difference represents a mean decrease in the men's pulse rates. And I just said before minus after, just to be extra clear, after exercise. All right, our procedure is a paired t-test for the mean differences in pulse rates. Random, it's given that the men were randomly selected. The paired data, it's helpful. Whenever you do a paired t-test, go ahead and say the data are paired, especially if they're before and after. So there's a good reason to pair them. Normal, well, the sample size is less than 30, so that could be a problem. What I'm going to do is and I'll show you on the next screen how I did it. I went and subtracted each person's and just found how much their pulse rate decreased. And when I did a histogram, this is what I got. Is it perfect? Nah, there's a gap, but nothing really crazy. So it does not show strong skew or outlier. So we're going to conclude that the normal condition is met. All right. Now, I'm going to show you how I can go ahead and get those mean differences. So what you can do is if you have list 1 has your before heart rates and list 2 has your after heart rates, if you go up here while you're up on top here and do list 1 minus list 2, it will calculate all the differences for you. Then once you do that, you go to a t-test. You'll notice on the calculator there's no such thing as a paired t-test. Well, the plain old t-test works, and that's probably why they don't call it like a one-samp t-test, is because you also use it for a paired t-test, so better not to have that named. Your mean is going to be 0 for this test. In this case, don't forget we're using list 3, our differences. Don't use one of these guys. And I'm saying that the differences are going to be positive. We're expecting this value to go down. And then, of course, you would go calculate. And when we do, here's our output. There's T, there's P. Degrees of freedom is pretty easy for me to figure out because there are 10 pairs. All right, so I'm not going to worry about, oh, where's my DF? So basically, label your outputs. Make sure you report T, report your p-value, report your degrees of freedom. See, I just took 1 off the 10. So now I can come to my conclusion. Because the p-value is lower than a reasonable alpha such as 0.05, we reject the null hypothesis. All right? There's sufficient evidence that the exercise machine lowers pulse rates. Now, I also ask you to interpret this p-value. What does 0.003 mean? All right. Well, assuming there's no difference in pulse rates, assuming that the null was true, there's this probability of getting this difference here, this mean difference of 2.8 in pulse rate or higher just by chance. Okay, and then lastly, I want to kind of wrap this up. This is all the different t-tests we've done, and it can be kind of confusing telling them apart. So you've got the one sample t-test for the mean, which we did in the previous lesson, right? And that formula was right there, okay? You have, in the conditions, I listed them all out. By the way, this is from your textbook, so I stole it out of there, and it's worth looking at. It's in the notes that I uploaded, so you can go ahead and look at those. That'd be very handy reference when you're working on problems. Okay, for a 2 sample, we have to have a difference of means, and our null is that they're equal to 0, all right? My null here is that my mean is some number, okay? And here's the formula, ugly, all right? And then this last one, which is a paired t-test, where we say the mean of the differences is 0. And the formula is a lot like this one, except we know the hypothesized value is 0. So you could almost really use this formula for that one and just understand that we're hypothesizing that the differences are 0, which is why you can use the same calculator function. Okay, finally, which test method do you choose? Well, it depends on how your data was obtained. So I'm going to take one situation and look at 3 different ways to get data and see how we would test it. So we're going to look at a shoe company that has designed a new sole, all right? And they decide to compare it to the previous sole design to see if it's faster. Assume it's like a tennis shoe or sports shoe. Determine the appropriate test method and state the hypotheses for each of the following. So they randomly assign shoes with identical appearance but different soles to a group of runners who have volunteered for the study and measure their times on the 100-yard dash. All right. Now, even if they had the same number of shoes in each group, that doesn't mean that this shoe goes with this runner goes with that runner's shoe time. You see what I'm saying? So there's no matching going on. And I definitely have two sets of data. So this is a 2-sample t-test for the mean old time minus the mean new time, and where the difference in mean 100-yard times for the old and new sole designs, all right? My null hypothesis, I could say, oh, that the old and the new are the same, all right? Or I could say 1 minus the other is 0. My alternate is that the mean old time is higher than my mean new time, okay? Now instead, let's say they have runners. They run once in each shoe design without telling them which is which, and they randomly assign whether the new design is used first or second, all right? Well, does one piece of data go with another piece of data? Yes. So if we have a runner, we'll call him Mike, and Mike runs with the old shoe first, that time is going to be compared to what he runs with the new shoe second. Now, to take into account, oh, but you could say, oh, he could be tired then. Well, what you do is you randomly assign. So half of the people are running with the old shoe first, half of the people are running with the new shoe first, so that it kind of takes that out of the design. It takes that variability out. So we're going to say this is a paired t-test for the mean difference in 100-yard times for the old and new sole design. So my hypothesis is that the mean difference is 0. My alternate is that it's greater than 0, that we actually did have that the new times are lower. So again, make sure you're kind of clear on what direction you're going there. So finally, let's say they don't have the old soles, but they knew that the average time was 27 seconds in the old soles. So in that case, we would just run a t-test for the mean time in the new soles, because we don't have any data to go. We don't have any old sole real data to go with the mean sole, the new sole data. Blah. All right, so my null is, oh, the time's going to still be an average of 27 seconds. And then my alternate is that they're going to save time on it, so they're going to take less time. It's going to be less than 27 seconds. So if you were doing this and you got to choose, which one would you choose? Personally, I think that the second one, the paired t-test, is great because it should have a much better shot at finding the smaller differences that you can get by taking the variability of different runners out. If you couldn't do this, but in this case you should be able to do this, if you couldn't do that, then I would say the first option, the 2-sample t-test, would be good. Unless, if you actually know the true average for the other thing you're comparing to, then in that case the third one is appropriate.